One last thing to mention, I think it's pretty impressive that Yoram both does excellent research as well as contributing to the engineering efforts at Google, actually working on the search engine and who knows what, probably not going to tell us, but I think that's really nice to hear from someone who has these two perspectives. So without further ado, let's start the presentation.
Thank you, Guy. It's always a pleasure to be back in academia. I've been alternating every 5 or 6 years between academia and industrial research, and it's been 6 years at Google. So talking about research in academia, let me first start with apology. About 3 days ago, I was coding my own code, semi-research, semi-production code at Google, but an engineer linked to my code, and I ended up breaking the code base of Google, and I got pager, people paged me in the middle of the night, and I had to sort of switch from working on the presentation to working on live code. So the apology is in the sense that my talk is going to be fairly mathematical, and I try to add some examples, but if you find it too difficult to digest mathematically, not Nina, of course, feel free to stop me and ask questions. It's a seminar, but I'd be happy to sort of cover less topics and convey the basic concepts I'm trying to talk about. This work, what I'm going to talk today, is completely joint work with John Ducci. John Ducci was an engineer for 1 year at Google, software engineer after his graduate studies, and he joined the PG program at Berkeley. He still worked with me on a weekly basis, 1 day a week at Google, and we do lots of formal research together. And what I'm going to talk today is mostly the formal research side in terms of experiments, real data. I'm going to give examples not from Google data, but from publicly available data. And one more list of acknowledgements before I start. Some of the research was done with Elad Hazan and Ambuj Tewari. Some of the old code and the roots of this research also go back to my days as a faculty. These are two of my ex-students, Shai Shalev, who's now professor at the Hebrew University, and Kobe Kramer, who's a professor at the Technion. And last but not least, partial list of people who work with me at Google, both on research and engineering. Of all this list, all of these people, just as an anecdote, hold a PhD, except for this guy. Hebrew name, but he's actually American. This guy doesn't have a PhD, but he was the world junior champion in chess. I think that there are far less world junior champions in chess than PhDs. He was the first American after Bobby Fischer. Between him and Bobby Fischer, there were only Russians. Okay, so after this long introduction, let me start with the outline, what I'm going to talk about. I'll try to present as gently as possible the notion of online convex optimization, and then I'm going to zoom into a specific apparatus, a specific framework called forward-backward splitting, or in short, Phobos. I'm going to describe a few applications of that framework and explain the experiments. After that, I will underscore the deficiency in this forward-backward splitting, and we'll talk about our next generation. This is actually the core algorithms that we use these days. It's called AdaGrad, adaptive gradient. And I'll describe AdaGrad, specific applications and experiments, and give some conclusions at the end. If some of the analysis is foreign to you, don't worry, the algorithms are actually very easy to implement, if not to understand. All right. So let me start. This slide is notationally heavy, but it sort of encompasses actually the core of lots of work in machine learning, and the concepts are pretty simple if you are used to them. And the setting is called online convex optimization. So on the left-hand side, I give the formal definition. On the right-hand side, I try to give quote-unquote examples or a specific example. So in this online convex optimization, this is a setting where we keep learning as time progresses. We get an example, informally, we get an example, we make a prediction. Based on our prediction, whether it's good or bad, we adapt our predictor, and then we get another example, and this process proceeds over and over. And we cannot talk about convergence often, although I will talk about convergence later on. So our goal is not to compare not to say how far we get to, say, an optimum of a function, but our goal is to say how well could we do in this online process where we never see the next example. We predict based only on the past in order to predict the future. How well can we do compared to basically an omniscient observer, someone who observes the entire sequence, can fix a predictor in this. This should be f of xt, that's a typo, f of xt, can fix a predictor f, and then we compete against this fixed predictor. So in the online learning setting, typically our predictor, we often talk about linear predictors. So the predictor is simply a weight vector. The inputs are features, measurements. The weight vector simply measures how important each feature is for the prediction. And then when we receive a function, we typically receive just a label. For instance, the features can be the pixels of an image. My weight vector is the importance weight of each pixel in the image in order to recognize the digit content of an image. And the label that we receive is the image, the digit content, whether it's a 0, 1, 2, etc. Once we receive the correct label, we suffer what we call a loss. So here's an example of a common loss in machine learning. It's called the hinge loss. It measures basically not only how good our prediction is, but also how confident we are in our prediction. And this term is called the regret. Again, this is f of xt. This is basically how much worse we're doing compared to this, what I call omniscient observer. There's someone who can fix f and choose the best f in hindsight. So again, I'm going to describe the set of parameters using the notation xt. ft is my current predictor, and I'm going to suffer loss based on my prediction ft on xt. The reason I chose x, this is actually more common notation in optimization. Okay, so this is the general framework that I'm going to use. Again, this framework, although it seems abstract, is very common and it's very useful. Think of, say, email spam filtering. We start with a weight vector, which is the importance of each word in our dictionary. We get an email. We try to predict whether it's spam or not by, say, routing it to a spam folder or keeping it in the inbox. And then based on the user feedback can be simply, mark it as spam or just read it. We can say whether the email is good or bad. That's the label y. And based on our prediction, we suffer some loss. The loss in the machine learning context is going to be some sort of a convex function that depends on the correct label and our prediction ft of xt. Okay? In the real world, the loss can be a discrete loss where we say, did we classify the email correctly or not? Okay? This framework also works for fixed f when we basically remove the time here, and then this is when it becomes optimization. But the techniques that I'm going to discuss today are applicable equally to the online learning and the optimization setting. It's easy to reason and to explain the online setting, at least for me, so I will focus on the online learning setting. Okay? But trying to connect these two areas, so when I say low regret, and if you come from numerical optimization field, low regret means fast rate of convergence. And the other way around. Okay. So now, saying that I'll focus on learning, let me actually go back to one of the oldest techniques in optimization in order to justify the online learning paradigm. And this is the online gradient descent setting, or online gradient projection. In this case, we say in this setting, we iteratively try to improve an objective function. And I don't write here the objective function, I just write here its gradient. So xt is my current estimate of the best parameters of the objective function. And at iteration t, I get some sort of an estimate of the gradient. So if it's a minimization, if it's a maximization problem, I would like to go in a direction opposite to the gradient, for instance. So I'm going to make some sort of a step along the inverse direction of the gradient. And this is xt minus gt times some scaling eta. And then I'm going to project back to a set of feasibility constraints. Often we would like to constrain the set of possible solutions. So this is this approach is called projected gradient, or projected online grad descent. It's very old. And one way to describe it, each iteration, instead of this projection operation, is each iteration simply solve this mini optimization problem within optimization problem, where we say, let's make a gradient step along the, let's move from the current point xt along the direction of the gradient gt, and then try to minimize, to find a point in my domain, this is my domain x, which maintains the minimum distance to this intermediate point. So this is just a way to view a classical algorithm. Nothing is new here, but this sort of view leads us, would lead us to our new algorithms. So an alternative view is for the same algorithm is as follows. Rather than, suppose we have this convex function f, we say, okay, let's build at the point xt, this is where we are, let's build a linear approximation. How does this linear approximation look like? If basically we make a linear approximation using the gradient at the point xt, this is simply a lower bound on the epigraph of f, okay? And then basically you can say, okay, what is the next step then? What is the projection step? It's basically saying, let's now build an upper bound at this point of the original function, okay, using this tangent point, and minimize this quadratic function. So in fact, this process, but what we're doing in this sort of projected gradient, we're building successive upper bounds on my convex objective function, where the upper bounds are quadratic functions. Quadratic functions are easy to minimize, and then I'm going to minimize this second step. Okay.
Is this constraint subspace a linear subspace?
This. In two dimensions, it's basically it is a line. In high dimensions, it's a vector in Rn, basically. Okay. All right. So now I'm going to talk a little bit of the analysis. This is actually what I call a sleep zone. If it's too difficult, you've never seen it before, yeah, just take it, and it's now 2 p.m. after lunch. You can take a nap for 5 minutes and engage back in 5 minutes from now. But let me talk for a second about the analysis to people actually who've seen this kind of stuff before. So what we get in this approach is what we call almost contraction. We're not necessarily getting close to the solution, but we're not getting too far away from the optimal solution. Meaning that if I look at the distance of is there a stick or a pointer? No. Never mind. If I look at the distance so x star is my optimum, okay, or the best solution that can be found in hindsight. If I look at the distance of xt plus 1, my new estimate to the optimum, it's not too far from basically where I was. Basically, it's the previous distance plus a term that depends on the difference between my function evaluated at the optimum and my function evaluated at the current point, plus a term, then this is why I call it almost a contraction, that depends on the norm of the gradient. Okay? And if you take the classical gradient descent proof, you can actually prove this sort of lemma using the approach that I've described. Now, if we sum over the time steps and just move things around, what we get is that this is what I call the regret. Basically, how far I am. So, and now I'm actually now I wrote the right term. So this is f. This is my performance, and this is the performance of the optimal solution. Now I can say that basically it's a constant term which depends on how far I started from the optimum, plus sum of gradient terms. So if I want to perform well, if I want to achieve fast convergence or low regret, what I want to do is to find a way to make the gradients as small as possible. Now, naturally, any process that converges to an optimum of a function, the gradients will get smaller and smaller. At the optimum, the gradients are 0. The question is, how can I do it fast? Okay? Now, classically, if I set eta to be roughly 1 over square root of t, I will get that the regret is square root of t, meaning that I will get, it will take me, if I want to get to epsilon close to the optimum, it will take me 1 over epsilon squared iteration, roughly. And this is pretty much classical theory. Okay. So now the next thing I want to do is to say, okay, this is a classical setting that talks about typically strictly convex functions. But often in machine learning, we would like to impose some structure of the problem. Now, a very trendy approach for imposing structure like sparsity, and I'm not going to talk about the theoretical foundations of theory of sparsity, just about the algorithmic part, is to add what we call regularization. And the classical form of regularization that promotes sparsity is called L1, which simply measure the sum of the absolute value of the weights. Okay, but L1 norm, the absolute value, is as a point of non-differentiability at 0, right? So we no longer can talk about gradients, but actually we need to sort of incorporate the tool of subgradient. So here's a short slide that shows you what a subgradient is. Go. It should have. Come on. All right. So if this is a point of singularity x0, so the subgradient set are all the basically vectors that are supported by a line that touches this. Okay, so this is a subgradient, and then if I basically rotate it, this is going to be a subgradient, right? So there is no longer a single possible direction when I talk about functions with singularities, and I need to adapt my methods, or the goal is to adapt classical methods to problems which have singularities like this. Now, what's the problem with subgradient? So let's have a look at two functions. This is, say, the L2, the x squared, basically. A very smooth function, very nice. And this is L1, the absolute value of a scalar, right? Now, if we look at the gradient of these two functions, the gradient of the squared functions are very informative. They get shorter the closer I get to the optimum. Okay? What about the subgradients of L1? They're always of the same length. Okay? And they're going to be of the same length even if I'm very, very close to the optimum here. Right? So if I'll take the classical gradient methods and make regular steps, I'm going to miss the most interesting point, okay, which is the 0 point in this case, okay? So what I really want is to take a classical method like subgradient method and adapt it to a machine learning setting which has typically a strictly convex function plus a function with singularities like L1, okay? So if previously we were interested in the regret analysis where we look at the difference between my performance compared to, say, what I call the omniscient observer, some x star here, okay? I'm no longer interested in a function, just the function f. I'm also interested in a fixed additional term, which I call here phi. It's in red. This phi of t can be viewed in the machine learning literature as the regularization. This is a term that is going to stay fixed along the course of the algorithm, and it will promote some sort of structure of solution. For instance, sparsity, or block sparsity, or hierarchy. There are different ways to impose structure. And I want to basically have an algorithm that has known regret, but will exploit the known structure of phi. For instance, if phi takes the form of an L1 norm. Okay? So our goal is again, to attain a small structured regret. And the algorithm is very, very simple. It actually consists of two steps. The first step I've already described, which is the unconstrained gradient step. So we do unconstrained, and when I say stochastic, it might be that my function, even in the optimization case, is very large. It's the sum of many repeating terms. Like, for instance, my prediction on many documents. So I have a very large collection. So I can get an estimate by taking a subset of my data and looking at my prediction on the subset of the documents. Oh, thanks. Okay. And the next step is I'm going to incorporate regularization. I'm going to take into account the structure of my problem. Okay. And this method is by actually no means new. It was somewhat reinvented over and over. I give here a partial list. It's similar to and that's why the name forward-backward splitting. That's the term that Lyons and Mercier used in '79. Nesterov gave an analysis of this specific method in 2007, Stephen Wright in '09, and in fact, Lin Xiao from MSR described yet another variant recently. What is new in our approach is the simplicity and the analysis and the view that I've presented, and I'm going to show it to you in a second. So, what is this Phobos algorithm? So, again, we're interested in minimizing this composite objective function, which has some loss function and a fixed, let's call it regularization. So if previously what we did, we said, okay, let's minimize, let's try if each iterate is a minimization between a quadratic function and a linear term that depends on the gradient. Now, the gradient, we don't want to take the gradient of my phi term, the non-smooth term. Now what I'm going to do, I'm going to break it into two parts. First one is the classical part, and I'm going to, rather than time-dependent estimate, I'm going to basically add the regularization as is. So I have a regularizer term and a gradient term, okay? And I'm going to solve this problem, okay? And so if this is my original approach, it's completely equivalent to saying the following. Let's solve the original approach, the original problem. This is just unconstrained gradient. And then add the regularization and then resolve the problem. Okay? So this is how simple it is. It looks maybe notational heavy, but it's it's going to result in very simple algorithms. Let me try to explain it pictorially. So basically, I'm going to try to minimize or to try to attain low regret with respect to a function f and a regularization term phi. And this is how their sum look like. Okay? And so what I'm going to do is I'm going to basically build this sort of quadratic approximation with the gradient, which is, this should be gt, which is time dependent, and a regularization term, which is, I'm going to incorporate over and over always the same way. Yes?
What's the reason why you did not linearize using the first order approximation of your regularization term?
Why can I not linearize it?
Yeah.
I can. In fact, if it's L1, it is piecewise linear to begin with.
I mean,
okay,
so
but
separate this two.
the reason I separate is that due to the fact that the regularization has a specific structure, rather than following the gradient of the regularization, I can solve it analytically once I build the approximation for the convex part. So I'm building a quadratic approximation to this function, and I'm using this function as is. Linear functions, for instance, are easier to work with. So I'm going to end up with a quadratic function plus a linear term due to the quadratic approximation, plus a linear term due to the L1, rather than putting everything in one big pot and managing them all together. What you're going to see in a second is that the end result is a very simple, not just a one algorithm. Give me different regularization functions and you'll get different algorithms. Okay, so why do we call it forward-looking? This is actually our contribution, our small contribution in retrospect. So if we look at what we do, we first take the gradient in time t and then we try to optimize. So what we get that due to optimality, we get that the zero vector is in the subset of solutions spanned by the subgradients of this equation. So what is written here? xt is my current estimate, xt plus 1 is my next estimate. This is the gradient of my objective function at the current point, and then surprisingly, and that's why I didn't linearize it, it turns out that this is the gradient of the regularization not at time t, not at step t, but actually at the forward point, t plus 1. So it's an odd-looking equation because, you know, I don't know where we're going. But if this is kind of in hindsight analysis, if we'll follow my scheme, what we end up is computing phi of t at the next point. Okay, meaning that we pick gradient f, the gradient of f from the current point, and the gradient of phi from the next point, although we don't know where it is, right? And so it's kind of a circular argument, but the fact that I broke it into 2 parts make it feasible. So what we get is that the new point depends on the previous point, its current gradient, and its future or forward regularization. Okay, and that's why we call it forward-looking or forward-backward splitting. Okay. So analysis-wise, things simply follow as before. I will skip it. It just says that, you know, whatever analysis you could apply before, you can still apply. And the same holds for regret. Let me skip that. So let me just summarize. Step 1, which I call t, which I denote as t plus 1/2. Just do an unconstrained gradient descent. Step 2, make a quadratic approximation, incorporate the regularization without any approximation as is, and just to perform this projection operation. Okay, and that's a general what I call an apparatus, because I haven't still specified what is phi of t, and how does the algorithm look like. So I'm going to show. Let me show just, you know, let me show L1 and skip L2, and talk about mixed norms possibly. Okay, so let me show what it does for L1. So all I need to do is actually to describe the second step. The first step is just gradient descent. So in the second step, basically I have, this is my quadratic function, and this is my L1 term. But this function, the nice part about it is that it is separable, meaning that I can work on each coordinate independently. It's simply the sum of the coordinate squares, and this is the sum of the absolute coordinates. So this is one term in the sum, okay? And it turns out, you know, this is a quadratic function with a piecewise linear addition that simply can be solved analytically, and the solution looks like this. We look at the sign of the intermediate point, and then we basically deduct minus lambda eta t, this is my learning rate, from the absolute value, and if it's smaller than 0, we truncate it at 0. So this is also called truncated gradient or shrinkage, and it was actually described multiple times. Again, these are the 3 most popular approaches that I found, but this is just one special case of our paradigm, and it just go through, and the analysis again is very simple. So what does just to summarize, what does this sort of gradient-based minimization with L1 term amount to? We go in the direction of the gradient, then we deduct this amount. So if we fall in this range, we say the current value is 0. If we don't, we just shrank the solution. So this is actually a good point to say, suppose I didn't take this approach. I just linearized everything as you suggested. What would have happened? What we would have got is non-sparse solutions, because again, we would have taken the gradient that includes the L1 term, and we would have missed the 0. So what we do here is we go along the gradient of the direction of the gradient. We deduct this term. If we end up in this region, we get true zeros. So the end result is an algorithm that gets me sparse solutions. If there is structure in the data in the sense that many features are irrelevant, we're going to get zeros here. Okay. Let me actually also discuss very briefly what happens with L2. If I use if we use L2, which is a strictly quadratic function, we get still a new algorithm. This algorithm amounts to scaling, so which means that at every step I make a step along the direction of the gradient, and then I scale. Okay, so in fact, this is actually a new algorithm for a well-established problem. I won't describe experiments with this, but it turns out that this approach is actually more stable than classical gradient-based approaches. This scaling, this shrinkage, actually provides some further numerical stability and better regret bounds. What happens if we use L2 and not L2 squared? So L2 is a cone. It has a singularity, it's 0. It turns out that what we get is an algorithm that does shrinkage. So ignore for a second this term, this plus term. So what we have here is that we take the intermediate term, the gradient term, and then we scale it by a scalar that takes this value. Okay, unless this entire value is negative, and then we set it to 0. So what we get is an algorithm that says either the solution is a scaled down version or it's an entire 0 solution. What's so good? There is nothing really good in this whole 0 solution. It has, if I tell you all the weights are 0 or unimportant, it's not a good algorithm. But if I actually I can use it as a building block, meaning that let me group the parameters into groups. For each group of parameters, I'll use this L2 norm regularization. What I can get is what we call group sparsity. So this is actually a slide about, say, grouping the parameters, which I'm going to skip. And let me talk a little bit about what do we do in high dimensions. So when the dimensions are high, and the dimensions can be, when I say high, I'm talking about more than millions of parameters, more than, say, tens of millions of parameters. And let me stop here. But when the dimensions are so high, it doesn't mean that every input, every example, has all the dimensions, all the features exist. For instance, let's talk about document classification. So when we do document classification, our features are the dictionary entries. Every word in the dictionary is a feature. So we can work with a dictionary of size, say, 100 million, or say 10 million. Why? Because there are so many different words in so many different languages and HTML tokens. So it's not unfeasible to have a dictionary of, say, of a few millions. But a given document of a length, let's say, 1,000 words cannot have more than 1,000 different non-zero tokens, right? So we're going to get very large vectors, very high dimensions, but very sparse. So here's like very toyish example. Here the dimension is 2, but this is typical case. If the examples are sparse, the gradients are sparse, and if we're going to use the algorithm verbatim, we're going to spend, every iteration is going to take us millions of operations, whereas, it should have taken just thousands of operations, right? So what we want to do is to basically ignore these sort of 0 columns and look at them only when we need them, okay? So for this reason, we want to basically, we wanted to develop what we call just-in-time updates, okay? Updates that depend only on the features which are on. And what helped us is the following proposition or lemma that says, suppose you want to do successive projections, okay? Instead of doing these successive steps, instead of doing these steps over and over and over, we can delay them. We can do lazy evaluation, and once we need to do a step, we can just accumulate all the step sizes that we had so far and solve this equation once, okay? This theorem, by the way, is surprisingly not true for any LP norm. It's true just for these 3 norms, 1, 2, and infinity. I tried to prove it for say, 3 and 4, and someone gave me a counterexample. Okay, so what does it imply in picture? What does it imply? So suppose we have this situation. So whenever we have zeros, we just skip we update this column and this column, and we just skip this column. Now, suddenly at time step 6, we get a non-zero gradient here. So what we do is simply fold all the terms, lambda t, from time 2 until time 6, because this was the first time it was 0, and this is the first time it was non-zero, and do a single update to this coordinate just at time 6. So all we need to do is just a simple bookkeeping. What were the step sizes that we performed along the run, which is very, very simple to maintain. Let me give a few experimental results, in fact just 2. I'm stuck? No. So here, just to illustrate the power of this. Now, again, the examples are with public available data. In fact, the 2 slides that I'm going to show now are, the data sets are by no means very large. They're not even large. But they're still are considered the staple of, say, let's call it machine learning papers or machine learning submissions. They're not necessarily good data sets in general, but they will still underscore the different properties of the algorithm. So if we want a one-word summary of this slide, us, them. Okay, that's the one-word summary. But what do we see here? So this is the algorithm that I've described, Phobos with L1. MNIST is a digit OCR data set. It's a digit classification problem. And what you see here are 3 different algorithms for roughly the same, for exactly the same objective function, but different methods. In blue, you see an algorithm called sparse due to Stephen Wright and colleagues, which attacks exactly the same problem, but doesn't have this nice, delicate analysis that we have. So it's, think about it as roughly the same algorithm without the insights that we got. And this is how much we gain. And in green, it's an entirely different family of algorithms. This is coordinate descent algorithm by the late Paul Tseng that goes one coordinate at a time. And then if you look at one coordinate at a time, sometimes you can find solutions analytically. And this is what was done here.
X-axis is 44.
Okay, so sorry. So this is the test error. This is how well we perform on test data. So I want to not necessarily just talk about convergence, but also about generalization. The x-axis is the approximate number of operations. And we try to be fair, meaning try to make this tight implementations of all these methods. They're actually very easy to... so you can think about it as, since they're all optimized the same objective function, asymptotically, if you take out the randomization, they should converge to the same point. So what we really want to show here is that whether we actually, in terms of rate of convergence or how fast we get to a good solution, how well do we perform? Yes?
Was the coordinate descent deterministic one or the stochastic one?
Despite the popular belief, it's not that big of a difference. But it was the randomized one. I mean, it was recently oversold that stochastic coordinate descent does much better than the cyclical one. I think it's overselling. This is just zooming in. These are actually the important iterations. After, by the time we get with Phobos to a good solution, there is still lots of time until we get to a good solution with the 2 other algorithms. So now, okay, let me give one more example. So I spoke about grouping the parameters. So this is not comparing different algorithms. This is the same algorithm, Phobos, but with different regularizations. So this is actually a result from real data. Here the data is large, but it's all compressed to a single slide. So when I say it's large, this is probably, if I remember correctly, this is something that Semi Benjo helped me with, all the images that from the web, basically, that Google collected from the web. And what we do here is just coding the images. So we want to code the images in a compact way, but we have some structure. Okay, what is the structure? For instance, all the images that came from the same query. So suppose you pose the query Nina. We're supposed to see pictures of Nina over and over and over, right? But these are faces of Nina, right? So they have lots of similarities. So we can compress them all together. No offense, of course, right? Right? And if I sort of pose another query, say cars or squash, I should get images. So what we would like to do is group-based compression. So how do we do group-based compression? We pose L2 regularization on all the images that belong to the same query, and then we try to find a compact representation. So what you see here is this Phobos algorithm when we impose a structure. So this is the error rate in reconstruction, and this is how sparse is our solution. And clearly, the denser the solution is, the lower the error rate. This is in logarithmic scale. But what you see here is a huge gap when we impose group sparsity and we don't use group sparsity. And that's another take-home message. We know how to basically use the structure of the data. And the algorithm that I've presented, or the framework that I've presented, enables very simple group sparsity. Okay. So now let me switch in the remaining time to the second topic of the talk that builds on the first, and try to illustrate the problem with sort of general gradient descent. So if the part so far is actually a variation of on a theme, this is basically a new view on a very old method. what I'm going to actually do now is a new view on a new on a very recent approach, and this is the algorithm which I called AdaGrad. But to illustrate it, let's look for a second at document classification. So this is a real document, okay, and you can tell what is the topic of the document from its content, but actually the most informative word for content prediction are actually the infrequent word. Word like, you know, the or and can appear in any document. So for instance here, the a very predictive word is Xerox, because for instance this word Xerox did not appear in Shakespeare's writings, right? And so it's very indicative that it's about technology, about maybe photocopiers. So the very infrequent words are typically the very predictive one. Okay, otherwise they wouldn't have been very infrequent. Okay, which means that if we look at the space, right, it's no longer spherical. If we look at, you know, the features determine the size of the space, so it looks very elongated. And so this space is typically hard to work with because, you know, there are very small changes with the infrequent features may result in very big changes in terms of our ability to predict well, but it's actually the frequent features that dominate the shape of the space, okay? What we would like to do is to work with such spaces. What we get is, you know, these spaces, okay? Numerically, what we see, if this is the label, so the label here is good or bad, positive or negative, there is everything is sort of drowns in noise, which are the frequent features, which can be non-informative. Word like and is non-informative, but it appears in every document, right? Whereas the infrequent feature that appear from time to time are actually very predictive. Let's look for, of course, it's a toyish example. Feature number 2, every time it's on, when I say on, it's one, means 1, the label is 1. The same holds for feature number 3. So what we would like to do is to reshape the space, but not a priori, but actually as we learn, because we don't know whenever we get one document at a time whether a word is going to be, frequent or infrequent, right? Like a word like Federer in Sport Illustrated in 1999 was very infrequent, but now every second document on tennis has the word Federer, so it's no longer a frequent, an infrequent word, right? So what we would like is to do is not to reshape the space, learn the space a posteriori. We would like to do it as part of the online learning process, and that's actually the challenge. So what I'm going to try to convince you in the remaining 7 minutes is that there is a simple way to do it. Okay. So, in terms of mathematical terms, I'm going to stick to my current framework. So that's the nice thing. We're actually going to basically build a continuum. We're going to start with Phobos, and we're going to move to this adaptive gradient method. So this is Phobos, what is written here. So what I would like to do is, instead of measuring the distance to the previous solution just by using Euclidean distance, I would like to define a distance based on a PSD matrix A. And the distance based on a distance is defined through an inner product space. So I'm going to actually talk about inner product spaces. So all I'm going to define is this inner product X. Dot X is defined through a matrix A, where A is PSD. Okay? And then I'm going to change the Phobos algorithm in only a single place. This is where it is changed. Everything is the same except for the way I measure the distances. Now, this matrix is going to play the opposite to play the opposite role to the distribution. It's going to take a very elongated space and make it spherical, so that the frequent features will get less emphasis, and or they're going to be de-emphasized, and the infrequent one are going to be emphasized. Now, let me skip the analysis. It just basically says that our goal is to work with A's, with matrix A's, which are we're going to make our gradients look small. So that's actually the design principle. If we can make our gradients, the normal fine gradients, be small, it will mean fast convergence or low regret rate. So again, you can ignore the top part. So how do we make the gradient small? Basically, if we look at our sequence of gradients and we stuck in retrospect, so this is a posteriori analysis. Suppose we can choose our matrix in hindsight. So this matrix A, we should minimize this term such that we want it to be positive, and then clearly if we find a matrix A which is good, we can keep increasing its norm, and therefore the norm of its inverse is going to get smaller and smaller, and we can minimize this term by taking it to 0 simply by increasing the norm of A. Therefore, I'm going to impose a constraint on A such that the total number of the sum of its eigenvalues is going to be bounded by some constancy. Okay, so if we know how to solve this part in an online fashion, so that I get estimates of A all the time, I can actually design an adaptive gradient algorithm that works well. Now, for general matrices, it's difficult, but if we focus only on diagonal matrices, it's very, very easy to solve that problem. It means that the matrix A, if it's diagonal, is simply zeros everywhere and set of scalars denoted here S1 through Sn. And if I need to solve this this problem, it turns out the solution, the jth component, the jth entry on the diagonal, is simply proportional to the L1 norm, not of the gradient, but the L1 norm of the jth component of the gradient that I got in time. So here's a picture. So if this is my problem, each row is an example. So these are the gradients. My scaling factors are proportional to the L1 norm of each vector. Okay, so I don't know why I wrote here 2, 1. So basically, this one should be proportional to root of 5. This is 1, and this is 1. So the number is there. So basically, it says that I'm going to scale down less the infrequent features. So that's basically, in words, the core of the algorithm. And so to recap, at time t, I just compute the time averaged, the L2 norm of the gradient, and I perform this Phobos step with a temporal matrix A of t. What this temporal matrix will do, it will push down the frequent features, meaning that I'm going to make smaller step for frequent features and larger step for infrequent features. And this is, by the way, very useful in truly online settings like online advertising. Every new advertisers, new words appear very frequently. Again, classical example, the word like iPad. Until 6 months ago, it never appeared, right? The day it appeared, many search engines, whenever you typed iPad, you got basically a query, right? Did you mean iPod? What you really want is within a minute of iPad queries not to say did you mean iPod, but actually give advertisements relevant to the word iPad. For instance, a new Samsung tablet, if you care about. So that's the algorithm. Let me skip the regret bound, which actually carries also some new news. And let me show you how this update look like when you talk about L1. So all it does, it basically says if you ignore the S's, this is Phobos. So all it does, it says, take each coordinate and scale it down by S. The larger S is, the smaller the steps are. The more frequent the feature is, the larger S is. So what we get is on-the-fly reshaping of the space, and we get this really fast converging algorithm when the space is elongated, when the space is non-spherical. So I think I'll stop with the formal part, and let me just discuss very briefly a few experimental results. So this slide is now I'm going to give examples of growing sizes. So this slide is about document classification. Here the problem is of moderate size. This is the RCV1, the Reuters Corpus 1 corpus. It has about 800,000 documents. The dimension is about 2 million. This is the number of word pairs. And the goal is to do document classification. And what you see here is the error rate across test classification error rate. And what you see in parentheses is the sparsity, meaning the percentage of non-zero parameters. So the lower the number, the better it is. It means that, for instance, in this case, it means that 10% of the parameters were said to be non-zero. What I compare here is really a nice algorithm called Arrow, which doesn't necessarily promote, which is not sparse, by Kramer. Passive-aggressive, also by Kramer and colleagues. Phobos, which I presented, and this adaptive gradient. And not only adaptive gradient is the best algorithm, it also gives the sparsest solutions, and you see also the improvement over Phobos, which is the non-adaptive part. So that's another take-home message: adapt. Okay. The last example that I want to give is actually pretty large. It's from an image set, ImageNet, which is available, which is publicly available. It has 15,000 object classes or queries. You can view it in different ways. Sami Benjo is at Google now, helped me prepare this data set. He actually works with these data sets and much larger scale data sets. And the goal here is to do image object recognition or image classification. And here's a table with result for precision at k. So the goal here, it's unlikely if you have 15 different classes and you get an image and you ask what is the object class of this image. It's very unlikely that with 15,000 classes you're going to predict the correct class, because two classes under car can be Camry and Corolla. So if you say that it's a Camry and it's a Corolla, it's not a big mistake. So what we want to do is to use ranking measures. Here, precision at k is how well do we do in terms of identifying the correct object class in the top k, where k can be a small number like 10. And here again, we compare the different algorithms, and so you see that these two algorithms, AdaGrad and Arrow, are the best performing one. These are the adaptive algorithms, the algorithms that adapt to the geometry of the space. Okay, I think I'll stop very soon. So just in summary, hopefully I was able to at least convey the basic ideas of a new apparatus for learning and optimization with structural assumptions. I described the framework, which is also applicable to other algorithms. If you'd like, you can go and look at the papers. One particular algorithm is the dual averaging of Nesterov, later adapted by Lin Xiao. And part of my research focus and engineering focus on efficient algorithms for very high dimensions. So things like lazy evaluation, which are not necessarily mathematically trivial, is part of the focus of this work. My current work is actually, I've been drafting in different directions that actually stem from this. I'm currently working on medium scale data sets where you want to understand more. So I'm working actually on new algorithms for decision trees that stem from this framework, and for maximum entropy methods. I'd be happy to discuss them offline. And just in summary, the talk today was mostly based on these two papers, two recent papers. And if you would like to read more, I basically created under my web page, I created a special section devoted just to sparsity, and you can read more from at that link. Thanks for your attention.
Any questions?
Can you comment on, I know you said that it would be difficult to consider an arbitrary matrix A in the last step.
Yes.
The diagonal matrix.
Yeah, but we can do arbitrary matrices as long as you can store them or at least find their inverse efficiently. So if you take, for instance, if a good compromise could be a block diagonal matrix. Okay? But in relatively small scale problems where you really want rapid convergence or high accuracy, like even signal processing problems with thousands of parameters where you can store 1,000 by 1,000 matrix, go for the full matrix case.
Okay, so it's really just the size.
It is the size and the time that it takes to take the inverse, actually. Right. 1 over s becomes the ij entry of the inverse matrix.
What if the dimension is very high, say millions of dimensions, then take just two norm of the gradient is takes a lot of time for each iteration.
So then this is actually, we also discussed it in the paper, it's not that expensive because what you need to keep is actually the 2 norm squared of each component of the gradient over time, which takes as many as number of features, so you just double the amount of memory, and then when you want to take on each iteration you just add another component to the 2 norm squared, but when you want to compute something you take the root of the norm squared of the gradient and you get it very efficiently. So you need to employ all of these sort of relatively simple data structures and numerical tricks in order to cope in I direction. But that's a good example of you can't really use it out of the bag the way the algorithm is described. But there are simple solutions.
When you had L2 norm regularization, there was L2 norm based and L2 norm square based. So what difference in terms of regularization in fact?
So L2 squared is a spherical, right? So if you look at the space, it's spherical. L2 is a conical case, right? So what happens is that if you're away from the point of singularity, L2 and L2 squared are roughly the same. But close to the singularity, there is a region of contraction where the L2 will zero out your solution. So by itself, it's not a useful regularization. But if you say, oh, let's take the parameter space and chunk it so that's into blocks. Each block I'm going to regularize using the L2, but I'm going to sum over the blocks. Now you get basically, in some blocks you'll get a dense solution like L2. In some other blocks, say, oh, all of this block is useless. It's all 0, which is very good when you want to tie parameters, when you want to group parameters and get sparse solutions.